when I was grading like homework 4 homework 4A, I think, and basically what we want to do is to find the number of sources, number of sinks in a DAG. And to do that, like it's very simple. We just simply count the number of just calculate the in degree of out and the out degree of each vertex to calculate it. But like I found some students like trying to apply the DFS with pre and post numbers. So that's to find the sink in the original graph and then reverse it and then again find the sink, use the same algorithm to find the sink of the reversed graph, which definitely works, but like given that it will definitely take a lot of lines of code, and when we were like, I mean, although the time complexity is the same, but like time complexity is not the only criteria for judging judging an algorithm and implementation of the algorithm. We also look at the whether the clarity of the code and the readability of the code and the space complexity maybe of the code. So try to write fewer lines of code if it's just a simple logic. And let's get started with today's material. So basically today we're going to talk about, just one sec, let me share the screen. Okay, so basically today we're going to talk about like dynamic programming. So let's take a look. Before we start with dynamic programming, I want to share some of my personal thoughts about like what is like dynamic programming here. So dynamic programming is kind of like there's some kind of similarity between dynamic programming and greedy algorithm. Basically, the first step is basically to divide the whole problems to smaller subproblems. And then the second step is to find an order to solve each one of the subproblems here. So subproblems. And then the last step is to solve like the future subproblems. After you solve each one of the subproblems, you want to store the value of it so that in the future you can use the result of the previous subproblems and basically solve subproblems, store them for future using. And like, let's take a look at the first question. You're given a n by n grid, which in this example here is just basically a 4x4 grid, right? And where each cell like has some of the gold coins, and we use like a 2D array T to represent the number of gold coins at each cell, and basically we start at A, which is the top left corner of the grid, and want to reach the bottom right here and end corner. And also we want to maximize the number of golden coins we can collect along the path. And also like the one constraint here is you can only move right or down each step. So basically here, this is one of the valid paths this way. This is also a valid path this way, but you cannot move like this. You cannot move up or move left. So I'll give you guys like 1 minute or maybe 3 minutes, within 3 minutes to think about like how to basically decompose this question into solve smaller subproblems. And then we'll basically go over this question. And also we have like a follow-up question, a modified version of this question 1A. Okay, let's take a look at the brute force way of doing that. So the brute force, basically we just explore all kinds of possibilities. We just explore all passes, like given a n by n grid, how many possibilities do we have? We're basically using combination of formula of combinations to show the total number of possibilities. So basically, since we can only go right and go down, and for example, we can only go right and down. So if this is an n by n grid, and since we cannot go outside of the bound, we cannot do this, we cannot go outside of it. So how many total moves can we make? So we can make n minus 1 horizontal moves, n minus 1 moves to the right, and n minus 1 moves to down. So basically, we totally we can make 2 times n minus 1 moves. And within each move, within these 2 times n minus 1 moves, we can basically let each, for example, we can let the first n minus 1 moves to go right, which is basically like this. And then the remaining n minus 1 moves will be go down, because we can only go right and down, and the number of moves going right cannot exceed n minus 1. So basically we're choosing n minus 1 moves from 2 times n minus 1 moves to go right, and this gives us the combination using the formula of combination. So basically we're choosing n minus 1 moves out of 2 times n minus 1 moves, and given the equation, we will have something like this. And this is like a huge number, and this is definitely an exponential time complexity, and the number of total possibilities is very huge. So we better come up with a more clever idea. And so basically, the intuition here is, if we look at the structure of the grid here, we can only reach x and y from the cell above him or from the cell left to him, basically these two cells here. Because we can only go right and only go down in this problem. So if we already computed the optimal cost to reach this point or this point, to reach these two cells, then we'll know the optimal cost to reach x and y. So basically, the optimal cost to reach x and y is basically the maximal value, the max of these two numbers, the optimal cost to reach these two cells plus the number of golden coins in xy. So this is basically the intuition about defining a subproblem. The whole problem is try to reach from top left to right to the bottom right corner, and we decompose these whole problem into little subproblems that we can solve more easily. And so the next step is to define the subproblems. And let's take a look at the definition is written right below it. So we define dpij. dp is basically the initial words for the initial letters for dynamic programming, and basically dpij means the maximum pass sum, which is also, we can say the maximum number of golden coins you can collect along the path to reach ij starting from 1, 1. So let me write it more clear. So if this is the grid, this is ij. Since we can only reach ij from these 2 points, so if we already computed the maximum path to go to this this cell and this cell. We can easily compute the maximum path to go to this ij. And our final final goal is basically to find the maximum path sum to reach NN. Okay, so let's move on. Let's take a look. The next step is to find a recursive formula and try to think what kind of in which order shall we solve these subproblems so that we can in the future subproblems we can use this, the result that has been pre-computed. It's kind of similar to like the Fibonacci sequence that we that professor discovered during the first lecture of this course. So the recursive formula is basically for each one of these, like since we define like dpij as the maximum path sum to reach ij starting from 1, 1. So dpij is basically if I and j is both equals to 1, that basically means you're at the initial point, then the maximum number of golden coins you can collect is T11. Otherwise, we basically check the maximum the best path to the cell left to yourself and the best path to the cell above you. And then we plus the number of golden coins inside xy or inside ij, inside your own cell. And so here we just, for convenience, we define, given that we have a 4x4 grid, this is the this is basically the coordinates of all those cells here. And we can like go over this example to see why, how it works. So basically, if we like, since our final goal is to calculate the maximum path sum from 1, 1 to 4, 4. So basically it is dp4, 4. What we need to do is first check the maximum path sum to the cell above him and left to him. And if we get the maximum path sum from 1, 1 to 4, 3 or 1, 1 to 3, 4, we can easily calculate the maximum path sum to 4, 4. So basically we're starting here and then we go here. And for 3, 4 here, we need to also check the cell left to him and the cell above him. Sorry, this should be this. We need to check like the maximum path sum to 3, 3 and 2, 4. And for 4, 3, similarly, we need to check the maximum path sum to 3, 3 and 4, 2. Like, as you can see, like we computed the maximum path sum to 3, 3 twice. And this, if we like, so like the key, another key feature of dynamic programming is to trade time with space. So basically, what we want to do is if we store like some of the pre-computed value, then we don't have to like compute it again. So we're using space to exchange more time. And so we computed like 3, 3 twice here. So basically, if we store this value, we don't have to compute it again. And what is the kind of order that that we should solve these subproblems, so that like the future subproblems can depend on the result of the previous subproblem. So if we start as 1, 1. So I'm sorry, if we start as 4, 4, we need these two values here. If we like start with 3, 4, we need these two values here. If we start with 4, 3, we need these two values here. So basically, you can see like the order is like this. If we want this value, we need to find something in this direction. So if we were computed everything from the beginning, we update the value here. since we can go only this way and this way, we update the value here. And then like the things will be very easy if like so basically this is the order that we should solve each subproblems. And as I mentioned, like since there are some overlapping subproblems, what we need to do is to store the value so that we don't have to compute it again. Very similar to Fibonacci sequence. We use like an array, but here we use like a 2D array. So let's take a look at the code here. So we use like a 2D array dp, where dpij is basically equivalent to dpij as we define, which is the maximum path sum from 1, 1 to ij. And then we initialize everything to 0 here. So as I mentioned, the order of solving this problem is going this way, this way, this way, row by row. We start with the first row here, and we start with the first column. If this is like if I equals 1 and j equals 1, that means we're at the initial position. We just update and the value as t11. Otherwise, we need to check like the maximum sum pass. First, we need to check whether there is a cell above us. Like if there's a cell above us, we try to update the maximum pass sum. And then if there's a cell left to us, we again try to update the value, update the maximum pass sum. So basically this is like what these two steps are doing here. Check whether there is a cell left to itself, and we'll check whether there's a cell above itself. And then like update the value. And also what we want to find is the maximum number of golden coins. So here we use max function. And very, very easy answer here. And the time complexity is very obvious that we have like we have a nested loop here. So definitely O n squared, given that like the grid is n by n. So if it's just basically some explanation here. So this is the original grid. This is our DP. If we start with initial point, then like in DP, since it's initial point, we just update the value as 2 as what is here. And it is 7. If we at this point, since like there are no cells above it, so we only need to, since the only way to get to this cell is from the cell left to it. So we update the value to, since this is 70 here, we update the value of 72. Similar here, since there are no cells left to this 100 here. So the only way to get to this cell is from above it. So we update the value to 102. But for this cell here, since we can go to this cell from here or from here, so we need to check which one of these cells can give us like get better value. Since here this is 102 is definitely larger than 72, so we update this to 102 plus 1, which is 103. And we keep doing this thing. We keep doing this thing like in which order? Basically, the order is like this. We do this line, finish this line, this line. Since like for example this line for this cell, since we have already computed everything here and everything here, and the pre-computed value, what we need, the pre-computed value we need is basically above it or left it. So we can basically simply update the value here. Very simple answer, and the final answer is 226. Okay, let's move on a little bit. Very, wait a sec. Yep. And let's take a look like an updated version of this problem. Very interesting. So right now, before we only have one, we only have one pass. We only need to look for one pass here. Right now, what if, let's use like, what if like there are two people trying to find the maximum number of goats, and one start as the bottom, as the top left here, and he wants to go to the bottom right. And oh, let me use like blue here. And there's another guy starting from the bottom left, wants to go to the top right. And everything the same as A. You're given an n by n grid, and each one of this cell represents like number of golden coins in it. But here we have like two different like explorers here, and we like again like we have like some constraints for this problem. So basically for A, we start with top left. You can only go right and go down. And for B, B starts at the bottom left. You can only go right and go up. And the constraint is A and B can only have one common square in their path. One common square in their path. So let me illustrate this. Illustrate this one common square here. So basically, I'll use like blue lines to represent the path of A, and red lines to represent the path of B. So if this is the path for A, and this is the path for B, then these two cells, let me use a different color. These two cells are two common cells, two common squares, we can say, in their path, which violates the constraint here. And similarly, if like, one sec, if we do this, and then all these three cells are I'm sorry, all these four cells are common squares that that is on the path, like on the path of A and on the path of B. So if we do this, we try something different. We start with here, we go down, and go down, go here. This is start. We start here for B, and then if we try this, then this will be try this kind of like option. This will be a valid solution, one of like the valid solution. I mean not solution, but like the path is consistent with the constraint, but that doesn't mean it's the optimal solution. So we only have one common square here, and this is consistent with the constraint. Very interesting problem. Given the time, we don't have too much time today. I will just like start explaining this. So basically the intuition here is, first, we observe that A and B must meet at least one square. Since the definition of meet is not basically it's basically they have like some common squares in their path. And since like our constraint is they can only have one common square, right? We assume like they meet at X and Y. And we use like blue for path A and red for path B. And let's like take a look at the following like possible situations. So if this is X and Y, and this is like the common square that they meet, X and Y, and if A enters from left and B enters from left too, since like for for A, it can only go right and go down. B can only go right and go up. So if they both comes from left, then this definitely violates the constraints, since this will also be a common square for both of them, right? And this is not something what we want. Okay, so the second situation is A enters from left here, and B enters from bottom from here. B enters from this direction. So for A, it can either goes right, or it can go down. And for B, it can go up or go right. And let's take a look like the following like different situations. So if A enters this way, and go down, then this will be another common square for A and B, since this is where B comes from, right? So since like A can only go down and go right, I'm sorry, go right and go down, yeah. And so B, the only option for B is basically go right, and let's go right. And similarly for B, if like it goes right after this, sorry. Similarly for B, the only, as you can see, the only option for B is basically it can only goes up. If you like observe it like more clearly, since A can only goes right, right? Since A cannot go down, so A can only go right. So for B, it can only go right and go up. Right now, like since A can only goes right, so B can only goes up in this situation. So we have like the first scenario where if like A and B enter like the common square in this way, then A can only keep its original direction, going right, and B has to keep its original direction going up. And this way, like they will only have like one common square, since from here right now, they will like B will keep going this direction and A will keep going this direction, and they will never have any common squares in the future. And similarly, let's take a look like the next kind of situation here. So basically, if A enters the common square, one of like, we assume like the X and Y is the first common square they have. If A enters the common square this way, and B enters the common square this way, and then similarly, we can have A can either go this way or go this way, while B can go, this way or this way. And we use like the same same trick to analyze this situation again. So B cannot go up, since this is where A comes from. So B can only go right. Since B can only go right, then A has to go down. Otherwise, they will have more than one common square, since X and Y has already been a common square of it. Okay, so after this, we basically like summarize two different situations, and like two different like meeting situation for A and B. So case one is basically if A enters left and leaves from right, then B has to enters from bottom and leaves from top. So basically they keep their original direction. They have to do this, otherwise they will somehow meet again. And case two is basically B enters left and leaves from right, and A enters from top and leaves from the bottom. And here we assume the meeting point is X and Y. So let's take a look at the optimal cost for case one. So we assume like this is 1, 1, this is N1, this is NN, this is 1N, which is the start of A and B, start of A and B, and the end of A and B. destination and use A prime and B prime. So for the optimal cost for case 1, which is A enters from left, we assume like X they meet at X and Y. And this X and Y can arbitrarily be any one of the nodes. I'm sorry, every one of the cell in this whole grid. And since sorry. So the best since the case 1 is A enters from left and leaves from right, so A will go here, somehow go here, and then leaves, and then go this way and leaves the common square in this direction, and then goes from here to the final destination. And for B, it will go this way, somehow goes here, and then leaves the common square and go this direction. This is the optimal cost for case 1. So the next step is for us to find the best path to reach from 1, 1 to x 1 minus 1, and to find the optimal path goes from y plus 1 to n to the destination of A. This is under the assumption that they meet at xy. And similarly, path B, same. And for case 2 is also very similar. I'll just quickly go over it. Start with 1, 1, and 1, 1 in. A enters here, somehow goes to this cell, leaves the common square this way and go here. And for B, same, goes here and leaves the common squares and goes here. And this is under assumption that they meet at xy. But given that they can meet like in every cell in xy except like the cell along the edges, since this is impossible. So what we next need to do is to apply the concept of dynamic programming. We basically compute and store entries in matrix DP row-wise, and we use DP1 to store the maximum path sum from 1, 1 to ij, only down and right. So since let me write it this way, just one sec. This is 1, 1. This is 1 in 1. This is ij. And for DP1, it needs to store the maximum path sum from 1, 1 to ij, only down and right. So basically, we need to store only down and right, like any one of the paths. But what we want to do is to find the maximum path that can go from 1, 1 to ij, and we store the value in DP1. And for DP2, we store the maximum path sum from nn to ij, or we can say from ij to nn, since like the order doesn't really matters here. So only up and left. Only up and left for nn to ij is basically only down and right here, maybe this way. And we use like DP3 to store the maximum path sum from n1 to ij, only up and right. And we finally do this. We store like the maximum path sum from ij to 1n, only up and right, which is basically 1n to ij, only down and left. Just a reverse order. And then after that, since like we were already seeing that like calculating the maximum path sum basically take like O(n) squared time. So to get the value of dp1, dp2, dp3, and dp4, basically all big O like 4n squared times. And the next step is basically we assume each one of these nodes inside the cell as the meeting point. If we assume this ij, we go over all ij, all possible meeting points, and we assume that this is the meeting point of them. And since if this is the meeting point of them, we compare like the case 1 and case 2, which has been defined early here, optimal cost for case 1 and case 2, and we find all the like the cells surrounded this ij. And then we compare like the case 1 cost and case 2 cost. So basically it will be starting point to get here and goes here, and the starting point goes here and goes here. This is the optimal, this is the case 1. And then we compare this and this. And since like these optimal cost has been like pre-computed in our in this step, so this is basically will take us one time, like one constant time, since basically we're just like get access to like a pre-computed value in an array. And then we compare the result we have like from all possible meeting points, and then after that we can get the optimal value. Because like we're a little bit short on time, if you have any questions, I will like answer after this discussion session, and we need to go on to the next question, which is also a very interesting question. So we have like 10 minutes, so I'll try to go over the concepts real quick. So the second question is, we have n words, and such that the eyes of the word is li. I want to print these words in the document to minimize the overall cost with the following constraints. There are at most D characters that can be printed in each line. So D characters. We have like at most D characters can be, and we assume that, one sec. We assume that D is larger than maximum of L1 to Ln, which is longer than the maximum length of all the words. And what we want to do is we want to find a way to print all those words so that to minimize the cost. And the cost is defined here. Basically, it is the number of extra spaces in the line. That's the square of number of extra spaces in the line. And the total cost is the sum of all the costs for all lines. And if we go over example, I think this question will be pretty clear. So we have like these 5 words, and the maximum number of words we can print is 7 in each line. And also, when we're printing each word, we need like, when we're printing 2 words, we need like one space between these 2 words. So if we do this way, if we print this in the first line, then there will be 3 extra spaces, since the maximum number of spaces is 7. And then we print is in the second line. And basically, since as I mentioned, there is an extra space here, so again we have like 3 extra spaces in the second line. And then we print sample in the third line, which is 1, 2, 3, 4, 5, 6, 6 spaces, and we have only 1 extra space. So the cost is 1 square. So here the cost is 3 square. Cost is also 3 square. So the last one is list, basically 4 spaces, and we only have like 3 extra spaces in the last line. So cost is again 3 squared. So the total cost is 9 plus 9 plus 1 plus 9, which is here. And you can go over like different kinds of like the way you arrange words in each line, and you can see. So for this example, the cost is 3 squared plus 5 squared plus 6 squared plus 1 plus 3 squared, and you can compute it. Definitely larger than 28. So how can we like solve this problem? Again, like if we like try brute force, then we have to go through every single possibility, every single combination. So that would probably take too much time. If like there are a lot, like a huge number of words in total. So what we want to do is to break this into smaller problems. And since here we want to print n word, and how many words should we print in the last line? And if we can print like the keywords, last keywords in the last line, like what are we left with? We're left with n minus keywords, right? So if we have already computed the optimal value, I mean the least amount of cost to print n minus keywords in previous, then we can just simply do this calculation in O1 time, right? So the subproblem we define here is we use DPI here to define the minimum cost. So basically it's written here, the minimum cost to print the first I words. And our objective is, given if there are n words, our objective is to find DPN, which is the minimum cost to print n words. And we use and the second step is to find a way to solve this subproblem. So we basically, if we want to solve DPN, we need DPN minus 1, right? So the order that we solve this problem is from 1 to n, and this way we can finally get the optimal value for DPN. Yeah. So let's define the recursive formula. So recursive formula is very important, and here it is basically the DPI, basically the optimal cost to print the first I words, basically the optimal cost to print the first j minus 1 words, plus the minimum value of like the cost to print the first j minus 1 words, plus the cost to print words j to word I in a single line. And we iterate from j equals 1 to j equals I here. And if we cannot print words j to I in a single line, then we basically return we use an infinite here to represent if we cannot print them in a single line. And since there's a minimum here, we will basically ignore this kind of invalid situation. And this is basically a recursive formula here. And so if we want to compute DPI here, we need the minimum cost to compute the first I minus 1 words plus the cost to print I to I, basically the I's word. And we need to compute if we compute the first I minus 2, compute the optimal cost to print the first I minus 2 words plus the cost. This should be minimum here, the cost of I minus 1 to I, blah, blah, blah. DP 0 plus the cost to print 1 to I. So this is all kinds of like all kinds of like possibilities we have. So basically, if we cannot, so for example, like we have a lot of words and we cannot print 1 to I in single line, then this will basically give us infinity. And given that we use a minimize here, so that doesn't really influence the result. Let's take a look at DPI minus 1. Similarly, minimum DPI minus 2 plus cost I minus 1, I minus 1. Given that we already like, here we already computed DPI minus 2, and here we need like this value again. So similarly, we use like a array to store all the pre-computed value. And this is like the last step of the dynamic programming algorithm design. So basically, here is the pseudocode for this algorithm. Since we're a little bit short on time, I encourage you guys to go over the pseudocode here. And since here, like we use like the time complexity O(n) cube, and there is like a better like improvement of the O(n) square algorithm that was mentioned here. Use a little trick to make it like more efficient, to make the time complexity more efficient. But like when we're like analyzing the after we finish analyzing the time complexity, we need to take a look at the space complexity. Also, since we use like a DP array here, a 2D DP array, so space complexity is also O(n) square. I'm sorry, we're using like a DP. I'm sorry, we're using 1D array. I'm sorry, so it is O of n time complexity. Okay, that's everything for today's material. Thank you guys for joining the discussion session. I'll stay here for minutes of 2 to answer any questions in terms of today's material or the homework that will due like in a few hours. You're welcome. Okay, no problem. I will wait here for let me stop recording.